Welcome to another class of analysis of Boolean functions. And in this class, I will cover chapters 1 and 2 of Ryan O'Donnell's book. And we will cover more or less the main definitions and the main results of chapters 1 and 2, and with some further reading exercise. Okay. So you can ask, what is a Boolean function? Let me define what a Boolean function is first. Okay, so you have here, this will be my standard notation for the Hamming cube. It just denotes the set, the n-dimensional set of vectors with only plus or minus 1 as entries. This is the Hamming cube. Okay. And then we have a Boolean function. It's just some function from the Hamming cube to a certain, to plus or minus 1, sorry. Okay. So we only have values at plus or minus 1. And sometimes we will identify this Hamming cube so sometimes we identify the Hamming cube by the field with 2 elements, which is just short for integers modulo 2, and this is often nice because, well, the identification here is the following: plus 1 gets identified with 0, and minus 1 gets identified with 1. And the reason for that is that here the additive structure gets mapped into the multiplicative structure here. Okay. So that's how you go from one to the other. And as a generic function from the Hamming cube is just some generic is just some function that takes complex values. Okay, that's the most generic function we'll be dealing here. Okay. And so a Boolean function can be identified as an electrical circuit because, for instance, you can imagine something like, so let me write here. You can be seen as an electric circuit. For instance, let's imagine that you have 4 inputs, and what you can do is that you, for instance, you can apply some AND gate here. See, I'm just randomly writing some things here, and then in here you can apply, say, a OR gate, and then you finally get your answer. Okay, and in here we are making the map, and for this thing we have to make a certain convention. We say that plus 1 means false and minus 1 means true, which in the same token is is when you do this mapping here with the 0 and 1, you also map 0 to false and 1 to true. Okay. So if that's the case, for instance, if I put, say, something like, say, 0, 1, 0, 0, for instance, and then what happens is what? At the AND gate, which has if both things are true, well, we don't have both things true, so this thing would be 0. And then you have 0, 0, and R of 0 is 0. So your function would be 0. Another example could be if I put 1 here, and then your function would be 1. Another example could be I put a 0 here and put a 1 here, then your AND gate is going to give you a 1. This is 0, and the OR is going to give you a 1 again. Okay, so and in general terms, you can write any Boolean function by applications of these AND and OR gates. So let me just, out of curiosity, let me just write what these gates are. So it's the AND gate of a vector X. Well, it's just it should be true. Let me assign it. It should be 1 if there is xi equals 1 and 0 otherwise. So this would map. So this is the using this identification. Boolean Hamming cube would have 2 and this identification here. Okay. And also this is the OR gate. And then the AND gate is the opposite. Is 1 if every xi equals 1 and 0 otherwise. Okay. So in that way, you can create a Boolean function. And you can show that any Boolean function can be created in such a way. And so this function here we wrote is what is OR of and x1, x2, and then x3, x4. That's the function we wrote here in this example. And now Boolean functions have multilinear polynomial expansions. So multilinear polynomials is just a polynomial P of x that can be expanded in the following way. So it's a sum that runs over the subsets of n, and n here will always be the set from 1 to n. And x to the power s, if s is a subset of n, is just the product of xi, I belonging to s. Okay. And great. So that's what a multilinear polynomial is. And theorem every f, generic f, can be expanded is a multilinear polynomial. And we always denote its coefficients by this. With unique f hat of s. Okay. And these are called the Fourier, also sometimes called the Fourier-Walsh coefficients. Okay. Why is that true? Again, I'm not going to give the proof here, but it's basically the reason that let me just give a short sketch of the proof. There are two ways of seeing that. One way of seeing that is that, for instance, what is the indicative function of a vector A? Well, that is this function here. So this is 1 if x equals A, and 0 if x different than A. Why? Because if I put xj equals to aj is either plus or minus 1. So A and the Hamming cube. So if aj is minus 1, and then say, and I put minus 1 here, this would be 1. And if aj is 1 and I put 1 here, this whole thing would be 1. But if it's the other way around, if this is 1 and this is minus 1, then this becomes 0. Okay. And so then you can write your function like this, definitely. But these are multilinear polynomials, obviously. And so therefore, this thing is a multilinear polynomial, so it can be written as this with some coefficients. Let me say bs, x to the s. And then it remains to show that these coefficients bs are unique. And this reason is because when you look at this set, this is orthogonal. Okay, this is orthogonal set with the inner product. Okay, and then you show that this is true. This is a calculation. You do this calculation and you conclude that it's basically because of the symmetry of the space. And then you show that it's orthogonal, and then you count how many guys are in here, exactly 2 to the n, because there are 2 to the n sets in there. And how many functions, different functions, can you create from the Hamming cube to the complex numbers? What's the dimension of this vector space? Because you now can multiply and add the functions because you're taking complex values. And the dimension of that space will be exactly the number of points in the set, it will be 2 to the n. And so the dimensions match. And so for this is a orthogonal basis for that space. And therefore any function can be written by least squares approximation. So then BS, so that would imply a specific formula that so the Fourier transform, which would be this guy, will have to be the sum Okay, and that would finish the proof. That would completely characterize these guys. Okay. Great. Let me just introduce some probabilistic notions. So I will always write like X like this to denote that X is, this would be short for saying that X is a random variable. Uniformly distributed in Hn. Okay. And sure. What else? And then we can introduce certain certain things. For instance, like, let me introduce here the inner product that I just used. So every object, every say operator or measure we define can be defined in two terms, either from a probabilistic point of view or from an analysis point of view, say. And you will see that more clearly in a moment. But for instance, the inner product I just defined above can be written now as the expectation of f times g, by meaning this is short for the expectation of f of x, g bar of x, where x is uniformly distributed in the Hamming cube. Okay. And of course, if it's uniformly distributed, I have to normalize by the number of points in the set. So I have a probability distribution, and that's where this 1 over 2 to the n comes from. Okay. It can define other things. It can define norms. So it can define the norm p of a function, which is just the expectation of the moduli raised to the p, and then I take 1 over p. What else? Oh, so what we observed before, maybe I should make a note here. What we observed before was that if I take x to the s, and I take, say, x to the s prime, and maintain a product of these two things, this is a delta of s comma s prime, which means it is 1 if the sets are equal and 0 if they're different. Okay, that's what I meant by this set of functions is orthogonal. Okay. Okay. And so, for instance, also, maybe I should just move this thing here a bit down and do one more thing. And then I can write the Fourier coefficient of a function just as the expectation of f times, right, like f of x, x to the s. Okay. There's another norm that you usually use here, which let me another observation. If we'll see, if f is Boolean, so whenever I say this, I mean that f. So if I don't say anything, then I mean that f could be any function from the Hamming cube to the complex numbers. But if I say it's Boolean, then I mean that f only has plus or minus 1 as values. Okay, so if f is Boolean, then you know that the expectation of f norm p, 1 over p, but this is always 1 because f only has plus or minus 1 as value. So this is always 1. So in particular, I can put 2 here, and this is 1. Okay, but now this is the L2 norm, and we have a basis for it. This thing has to be equal, and this is Plancherel. That is, whenever you have like a sum of the squares on one side equal to another sum of the squares on another side, we'll say that's Plancherel's identity. I mean, that's kind of weird, but everyone follows these notations. So I guess we will be stuck with this Plancherel word for the rest of our lives whenever we see it squares in one side and squares in another. But in any case, this has to be this. This has to be the sum of the squares of the Fourier coefficients. And we actually know, I forgot to say, this is more than just a orthogonal basis, is a orthonormal. Because this is actually a delta, okay? So it is the norm of each of these functions are 1. And so in particular, that's what you get exactly this. Okay, otherwise you had to multiply by the norm of these functions, but it is 1. Okay. So so this is nice because you can also interpret, okay, so the sum of the squares is always 1. So you can interpret this, you can interpret a Boolean function as a distribution over a certain graph. Okay. So let me write this here. So we can see f Boolean as a distribution over the graph G, which has vertices and edges. The vertices are just the subsets of n, and the edges are pairs of sets, such that S is contained in S prime. Okay, so the drawing you should keep in mind is something like this, where I do know that S is contained in S2 primes, S prime is contained in S2 primes, and S contained in S prime. Okay, so you draw the arrows pointing to, so it's a direct graph, the directional, there is a direction to the edges, okay? Okay, and then you put here the weight so then the weight in S will be this guy. So the sum of the squares of the weights is 1, so it's a distribution on the set of weights. And so one can so one can interpret this as the a probability distribution, and so on the space of weights. Okay, that's what I wanted to say. What else? Yes. Okay. There are more things that I want you to find. Okay. Oh, maybe all these things you can figure out. Okay, let me define other probabilistic notions. These are norms. Let me define variance. So what's the variance? So variance of a function f is what? Is the expectation of f of x minus the expectation of f squared, which we can always simplify to squared, which by Poincaré has another and in here so this is the first part, and then in here you're just removing. So what's the expectation of f is this guy here is just f hat of the empty set, so removing that from here, so it's s non-empty. Okay. Yes, you also have so what happens if f is Boolean? I mean, maybe. So some things simplify when f is Boolean. So if f is Boolean, for instance, what is the variance of f? And then we let this as an exercise to show that is actually equal, and then show this probability that f is 1 times the probability that f equals minus 1. Okay. Let me define covariance. What's the covariance between two functions? Well, it's well understood to be what? The inner product, which would be then the expectation of f minus the expectation of f times g minus the expectation of g. Just a bilinear version of the variance. And I would put bar here to deal with the complex case, which you can further simplify as well. Should be this. And then you can also further simplify by Poincaré. Okay. Yep. So there is these probabilistic notions, and there was one more thing that I would like to define: variance, covariance, inner product norms. Okay, so far so good. Let me see what else. Oh, so another thing that I want to define is the distance of two functions. And so by definition, this would be the probability that f is not g. Okay. So again, this is a probability of an event. So that means this is by definition the probability of fx different than g of x. Of x is uniform when x is uniformly distributed in the Hamming cube. And whenever you have an event, you can measure this as the expectation of the indicator function of that event. So now this is a random variable as well. They will create it using fg and the random variable x, and then you can compute the expectation. But if you open this thing, this would be exactly the x's in the Hamming cube such that f of x is different than g of x, and you're just summating one. Okay. And there was a nice result in chapter 2, which you will write here, which is the BRL test. This is short for Bloom, Lube, and Rubinfeld test. It's to test when something is linear. And in here, I have to use the identification. And so I will have a function. So this will be for a function in here to the set 0, 1. Okay. And what is the test? Well, step 1, so let x be uniformly distributed, say x and y. Then you query f of x, then f of y, then f of x plus y. Now I can do f of x plus y because I have a summation structure here. And then we accept if f of x plus y equals f of x plus f of y. And now I have to, well, these functions have values only in plus or minus 1. So this summation here has to be equal modulo 2. Okay, and I prefer to state in this way than to put here f2, okay? And great, so the theorem says, so this is the test. And so the theorem says, if BRL, BLR, of course, has to be in alphabetical order, BLR. If the BLR test accepts F with probability greater or equal than 1 minus epsilon, then there exists a linear G such that distance of F to G is less or equal than epsilon. Okay. So what's the BRL test? Is to test when a function is close to being linear. And what you can do is simply you randomly select inputs n, x, and y, uniformly distributed, and you test when this happens. And if this happens 1 minus epsilon % of the time, then that means that you can actually cook up a G such that the distance of F to G is less or equal than epsilon. Okay. So it's G linear. Okay, but maybe I should say what it means to be linear. The obvious thing, okay? That's what it means to be linear. And I'm not going to show this result. You can read it on the book, but it's a short proof, but it's a nice application of the probabilistic method. Okay, so let's continue with some important definitions. And these will be getting in the world of measures of complexity. So one of the main parts of this field of analysis of functions in the Hamming cube is to study their complexity. Okay, so there are several measures of complexity that we will see during this course, and this is just like the very first one of them, at least in the following the book. So what's the influence of a variable? Okay. That would be what you want to compute what's the probability that if you flip the variable xi, so let me use that notation, xi goes to minus xi. Okay. And x is uniformly distributed in the Hamming cube. So you want to know what's the probability of that the value of the function change. So you take the variable xi, you flip it by -1 and by the opposite sign, and you measure the probability of this change. So if you open this probability, what you see is that this is exactly where here I'm flipping, let's see, wait, okay, I'm flipping xi. Okay, so you take all the x's for which if you put +1 in one variable, and if you put in the variable I, and if you put -1 in the variable I, the value changes. So that will be the influence of the variable I, and then the total influence is just the sum of the influence of each variable. Okay. Okay, there is a way of measuring this total influence in terms of derivatives. So let me define the derivative. di of x, so derivative in the direction x, direction I, that would be what? F of x when you send xi to 1 minus f of x when you send xi to -1, and you make this difference. Okay, that will be the, say, discrete derivative. And so if f is Boolean, di of f of x. So notice that di of x is actually depends only on n-1 variables. It doesn't depend on the xi variable anymore. Okay, that's something to note. So this would be 0 if f of x, when you flip I, this is equal to f of x. So if you flip I and it doesn't matter, then it's 0, and it will be 1 when this is different. Okay, and so in that way, if f is Boolean, then the influence of, this is for f Boolean, is just the expectation of the moduli c squared of the derivative. Is this squared of the derivative. Okay. And what, so this is, but then what happens? Well, then we can we compute the Fourier expansion of the derivative? And the answer is yes. And then we leave that as an exercise, but it's not hard to compute. Could be that. So you would be only the summation of the sets that have I, and then you go ahead and remove that I from the set. As I said, this guy cannot, it only depends on, it doesn't depend on xi anymore. So that's why we remove the I from these sets. Okay. And so therefore, we can write what is this thing is in terms of Fourier transform, in terms of Fourier coefficients. This would be that, okay? And so you can also conclude that the total influence will be then a summation of these things, which will be exactly thus in this computation. Okay. Yes, and so yes, so here, okay, so here I should go back and I should say F Boolean here. This is F Boolean. So if F is not Boolean, okay, so F is Boolean, you define influence like this. But if F is not Boolean, then the way to define influence is by this. Okay, so you can compute a derivative. You don't know if it has this identity, but in any case, you define it like this so that the influence is this and this. So let me write that remark. So this is how do you define influence in general. Okay. Yes. What else? Okay, there is another. So there is another way of say total influence if F is Boolean. What's the total influence for F is Boolean? What we just computed is this sum. In general, is this sum given by this, or is the sum of these things? But if F is Boolean, you can interpret. So you have that graph G, which is given by well, the vertices will be subsets of n, and the edges will be given by inclusion, as I said. And you have here a distribution, which is given by this, because since F is Boolean, the sum of these things are 1. So this is the weight of the vertex S. And then you can think of what is the influence of F as a probabilistic expectation. So this would be what? The expectation of moduli of S when S is uniformly distributed in, say, this graph. Let me write it as G of F. Okay, so this whole thing here, let me call it G of F, which is the graph with this weight. And if you take a random variable which has values in the vertex of this set with this distribution as weight, so it's uniformly is distributed as the distribution over the graph of F, and I compute the expectation of this would be exactly this guy here, because just multiply by the value times the probability distribution in summation. Okay, so this is another interpretation of total influence when F is Boolean. There is another way of computing influence. This is using the Laplacian. And so what's the Laplacian in the direction I is just F minus the expectation of the variable in the direction I, and this guy here is just equal to f of x, xi equals 1, plus f of x, xi equals minus 1. And you take the average of that, okay? And so this is Laplacian direction I, Laplacian I, say. And so the Laplacian will be just L of F, would be the sum of these guys, which will be what? It will be N F minus the sum of EI of F. And what you can show is that to say exercise, you can show that the influence I of F is just Li of F times Li of F, which is also equal to Li of F times F. And the total influence of your function is also given in terms of the Laplacian. Yes, I think this is this should be just this. It's just this. This is just the sum. If I summate the Li, you'll be summating the i's, and okay, this has to be this, which is also yes. Okay. And so, so another way of computing influence is computing the Laplacian. Okay, what else I want to say? And there is a nice result you can show, is that theorem, more like a proposition, that the influence of F is less or equal than the influence of the majority function. We'll define what majority is. And this is about square root of 2n over pi, 1 plus O of 1 over n. And where majority, so this happens if F is monotone. Okay, so what monotone means that f of x is less or equal than f of y if x is less or equal than y. So it should say here Yes. And here monotone means this. And what else? And majority of X is just the sign of the sum of the variables. Okay, so if the majority votes +1, and then it's +1. If the majority votes -1, and it's -1. Okay, this is another cool exercise to do. Okay, let me define some other things. Noise stability. So the noise stability delta of a function f is the probability that f of x is different than f of nx, where x is uniformly distributed in Hamming cube and n is uniformly distributed, but it is a biased random variable. I would say that what this is in a moment. And so this thing here is multiplication coordinate wise, and n is just the noise, and these are, of course, IID, and so identically independently distributed, and the probability of ni being -1 is delta, and the probability of ni being 1 is 1 minus delta. And this is just encoded by saying this. Okay. So what you're doing here, you're taking a function, and here's the value of your function, and then you're flipping some of their entries by probability delta, because delta is the probability that this is -1, and you're computing what's the probability of changing the value. So that is, in the presence of noise in the input, is the function nicely stable? Say, is this small? That's the question. And so there you go. This is the definition. Yes, but what else I want? Okay, so then we show the following, and this is Perry's result. Term. You can read directly in his paper, which is noise stability for the weighted majority. That's the name of his paper. Or you can also read in chapter 5 of the book. Of Ryan O'Donnell's book. And what is the result? So if you have a weighted majority, so instead of now counting majority, you count with a certain weight, and you have a certain order threshold. Okay, if this weighted sum is let me put minus here, is above t, then you get +1. If it's below t, then -1. Okay, so you can interpret this as a kind of a voting rule. For instance, in the United States, is more or less like this: every county has their weight, and then the votes are of the county accounted according to their weight, and that's how the votes are. That's how they sum the votes. So for instance, there were cases where a certain candidate had more votes in general, but he didn't win the election because when you do the weighted sum, he actually lost. Okay, I think that happened with Trump and Hillary as well. So I think Hillary got more votes, but if you count with their accounting system, than trump 1. But in any case, Paris showed what happens if there is noise in this, let's say, calculation of the votes. What happens if some of these votes are flipped, okay, with a certain small probability. So then Paris shows that the probability of majority WT of X be different than majority of WT of NX, X uniformly distributed and N biased as a noise that is less or equal than some constant square root of delta. Okay, universal constant. That's what it shows. Okay, so for all these voting rules, if you randomly flip some of the votes, then you have to account for, if the probability of flipping is very small, then the probability of changing the outcome, the result of the election is also small because it's bounded by square root of delta. Okay, and that's best possible. Okay, because this is best possible because if you just use the majority function without any weight and without any threshold, you can show, and you divide this by, you can show that this converges to, if I'm not mistaken, is something like square root of 2 over pi maybe it's 2 over pi. Yes, it's 2 over pi square root of delta 1 plus some O of delta. Yes. And this is just basically implied by the central limit theorem. Okay. So in the actual majority case, that square root of delta is the best you can do. Okay. And I give this as a reading exercise. You can go to chapter 5 and read the proof, which is different from the original proof of Paris. So maybe you can read both proofs. Okay. And what else? Oh, there is another way of representing. That will be more important later, but I can. So there is another way of representing the noise operator. So let me define T whole. And then we will see this operator T whole more often in the when we study hypercontractivity. Okay, so you go to the Fourier setting and you multiply by something. Okay, so this T whole has this nice property that is has a structure of a group representation, because if you do T whole 1, T whole 2, that is just the composition. Okay. And there is another nice way of writing yes, there is another nice way of writing this T whole operator as an expectation. And so say that Y is, say, rho correlated to x. So you fix a point x and you say that y is rho correlated to x if the probability of yi being xi is this. This was a minus here. Okay, so you fix a point x and you take a random variable y and you say that y is co-correlated. This is just my abbreviation to correlated to x if that happens. Okay, and then you can try to measure what's the expectation of f of y given that y is co-correlated to x. Okay, so this will be a function of x because x is fixed and then you do an average. So what that would be, well, I can just expand first f in terms of its Fourier series. And this will, since this y is, of course, I'm taking each coordinate to be independent. So this would be just that. Okay, and then you can compute what this is. Let me compute it fast. What is the expectation of y? So it'll be xi I have, and then minus xi, the same with the minus, and this will be what? This will give exactly what? Xi with this cancels and you get just xi times rho. And so you get exactly rho to the s, x to the power s, which is Tf of rho of x. So in particular, if what you deduce is the following, that T rho of x in moduli what do I want to say here? Yes, the whole of x in moduli, what is this? This is the expectation in moduli of f of y. Y is rho correlated to the point x, but this is definitely less or equal than moduli of f of y, the same thing. But this is what? This is T rho of f moduli of f in the point x. And this holds, of course, if rho is real. I'm assuming that rho is, okay, this I have to assume. So this is in principle defined for every, then I have to assume that rho is this. Okay, so this is in principle defined for any complex rho. But now if it's between 0 and 1, then I can define these probabilities. And then I can do that. And then you have this identity, this inequality, which not, I mean, if I just ask you to prove that, they will be, well, how can I show that? It's kind of weird. And it's just because if you represent in terms of expectation, what you're actually doing is representing this operator as an integral against the kernel. And that kernel is positive. And so then you can move the moduli to the inside. And that's why you have this, okay? Okay, and these operators will show up again later on when we talk about hypercontractivity results. Okay, that's more or less what I wanted to show. There are other nice results in these two first chapters. I recommend you to read chapters 1 and 2, and also yeah, and that's basically it. And then I'll see you in the next class. Thank you.